Normalization is an essential part of modern transformers. But since everyone tells us to question everything, let's ask a simple question. Do transformers actually need normalization layers? For years, normalization has been treated as essential in deep learning. Batch norm, layer norm, RMS norm, almost every modern architecture depends on them. The common belief is simple. Without normalization, deep neural networks become unstable. But this paper challenges that assumption with a very unexpected idea. In transformers, layer normalization takes activations and does two things. It keeps values in a reasonable range and suppresses extreme values that could destabilize trading. Mathematically, it computes statistics like the mean and the variance, and in other words, first and second order statistics for every token and then normalizes the activations. This sounds complicated, so let's step back and ask a deeper question. What does layer norm actually look like as a function? When the authors plotted the input values versus output values from trained models from vision transformers to ResNet, they observed something really interesting. Instead of behaving like a pure linear operation, LayerNorm produces an S-shaped curve, as you can see here. We usually assume LayerNorm is almost linear because scaling and shifting are linear operations. But because normalization depends on computed statistics, the overall behavior becomes nonlinear. The resulting curve closely resembles a tanh function. Small values pass through almost linearly and unaffected, while large values get smoothly squashed. Extreme activations are compressed. This leads to an important insight. Normalization might not be special because of statistics, it might be special because it squashes activations. If LayerNorm behaves like a tanh curve, then a critical question emerges. Maybe we don't need normalization at all. Maybe we only needed a function that scales activations appropriately and gently limits extreme values. This leads to the main idea, Dynamic Tanh or DyT. DyT replaces normalization with a simple operation, the tanh function, where here the alpha is a learnable scaling parameter. That's it. No mean computation, no variance estimation, no batch statistics. Just scale the input, pass it to the tanh, and apply a learnable scan and shift, and that is pretty much optional. So why does this work? Think of neural network activations like water flowing through pipes. Normalization constantly measures the flow rate and adjusts it mathematically. DyT instead installs a smart valve. Small flows pass freely while large flows are smoothly limited. Stability emerges naturally as the network learns the correct scaling during trading. The deeper implication is powerful. Normalization layers require computing statistics, but this work suggests that they may not be fundamentally necessary. The key takeaway is that transformers might not rely on normalization itself, but on the behavior that normalization creates, the squashing behavior.